Hey guys, welcome back. In today's video, I'm going to be showing you guys a back test I did seeking to find the best days to sell option premiums, specifically on puts. So things we're going to be considering are the deltas, the number of days left to expiration. We're also going to be taking a look at how far the strike is from the underlying. Now the first thing we're going to need is to require some packages and also some sort of database for the options. For this particular tutorial, I'm going to be using Palantir as an example since the stock price is not that high, making it a little bit more feasible to sell put options. So I commented out the code that gets this options data from my database, and I'll go ahead and show you guys what the data looks like. I don't use the IV, but it may be worth looking into. We also have the theta, the option contract name in full, the delta, the expiration, the flag, whether it's a call or a put, the strike, where the stock closed, the trading date for this particular quote, the number of days left to expiration, the mid price for the option, and lastly, the underlying symbol. I'm going to start this back test from the beginning of the year, and that's why we have a considerable amount of entries here. So back in our script, once you have read in your options data and the columns we need, we're going to extract the unique trading days in our data set, and for reference I'm using end of day data for the options collected from the CBOE, and I'm also going to split the data at the 70% mark of the length of our dates, and that's to make sure that we have a test set which we're going to use to run our back test, and then our validation set, which I'm not going to be using in this example since the optimization was taking too long, but I'll go ahead and show you guys what I did. So to create the optimization wrapper, where we're going to focus on four things, which are the delta, the open and close days to expiration, and lastly the percentage to the strike. So we want to consider options that have a specific delta, which will be at or below that delta. Typically the lower the delta on the put side, the further away it is from the at the money strike. The days to expiration are pretty self-explanatory. So if the number of days to expiration on the open is 25, we're going to try and find a put option that's selling around the same number of days to expiration. Same thing for the closed DTE. If the closed DTE was 10, we're going to try and find the option we opened and see what the mid price was around that DTE, and we're using approximates since we do have to consider weekends and holidays. And lastly, the percentage to the strike, which is how far the stock has to be from the strike that we opened. So all of those will get passed into this function along with trading dates, which is just the vector of dates we want to try and find options for. And if we go ahead and open up this function, we're going to pass in each unique trading day into this function, and what it's going to end up doing is going to subset our main data frame with all of our options that meet the criteria that we pass in. So most of this stuff is just subsetting and making sure it meets our conditions. In this back test, we're going to hypothetically try and sell premium each day, and later down the script I'm going to be showing you guys how to narrow down the results, since ideally we won't be trading every day. So by using this function, we're going to go ahead and pass it in to this lapply. We're going to pass in the vector of trading days and extract the P&L, assuming there's no errors. And then finally we're just going to roll by our results and return that as a data frame. Now that we have that wrapper, we can go ahead and set our optimization parameters. We're going to extract our dates for the validation and testing sets. Since I'm going to be using DE Optim, I need to set the lower and upper bounds for each of the parameters. So how this works is for the first parameter, which is deltas, we need to set the minimum and upper bands. So we're going to use 5 and 70. For the number of days to open up the option contract, we're going to use a minimum of 20 and up to 70 days. And for the closing DTE, we're going to hold down to 5 for the minimum, or 25. Now it gets a little bit tricky here since there's an overlap, but in the actual optimization function, I'm going to make sure that our number of days to expiration on the open is higher than the close. Now lastly, the percentage difference from the strike to the underlying price will be a minimum of 5% all the way up to 60. So the strike that we choose has to be at least this much away from the underlying price. And now we have to build a function to round these numbers for the optimization. So for the first and last parameter, we're going to round everything to 2 decimal places, while we want to keep the middle, or the number of days to expiration, rounded to 0 or whole numbers. And the function that we want to optimize will be toOptim. So it's going to pass in a vector of parameters to use, and we're going to make sure that the number of days to expiration on the open is higher than the close. We're going to try and run our function that we built in the last block, and if it didn't encounter any errors, this should not be here. It's going to go ahead and return the Sharpe ratio. Otherwise, it's going to set the Sharpe equal to 100. And since we're minimizing, this has to be set to negative so that it's actually maximizing our Sharpe ratio. Otherwise, if the number of days to expiration on the open is less than the close, it'll also return a Sharpe of 100. Once we have defined our parameters and built our optimization function, we can actually go ahead and start the optimization. Alright, so to run the optimization, it's fairly simple. All we need to pass in is the optimization function, our lower and upper bounds. And for the control list, you want to make sure that the iterations are considerably high. So I'm just going to set that equal to 100. And we also need to set our rounding function as the FN map. So what you see in the printout is it'll iterate as it tries to optimize by passing in certain values for the parameters. So it'll go from 1 to the number of iterations in iter max. And it'll go ahead and print out these values. So the first one would be our deltas. The second would be our days to expiration at the open, so it's saying 26 days at least, and we close at 15, and it has to be at a minimum distance of 10%. So it'll go ahead and scan through and return the Sharpe ratio at that given parameter list. So I ended up pausing or halting the process since it did take too long to run and it was not going to finish on time. So what I ended up doing was replacing the optimization values by this current set. So I set the deltas equal to 50. The minimum days to expiration at the open are 30. We close at 20. So we only hold for 10 days and the maximum percentage will be 10%. And once we extract those values, we can go ahead and plug them into our original function called sell puts. So this is the cumulative sum of the option premium we collected if we did this every day. Since that's not particularly realistic, and I went ahead and split it by actual days of the week. So here in this table, we see the days of the week, the sum of the premiums, and the average return. So it looks like Thursdays was particularly good. Now, if we were to only plot Thursdays, we get this chart here, which we see was particularly profitable. Now, ideally, we would want to use our optimization results and plot this to see how well it performed at a sample as well. Well, with that, guys, this concludes the video. I hope this was useful information. I'll leave a link down in the description area to the Patreon where you can find the script. Please consider subscribing to the channel if you haven't done so already. Thank you so much for watching, and I'll see you guys in the next video.